Okay, so we're back on our lecture on the chapter 4. And in the previous discussion, we talked about the strains placed on our cyclic compounds. There are two types of strains. We've learned about the angle strain and we have the torsional strain for the different cyclic compounds. And we've studied that from the cyclopropane, cyclobutane, and then cyclopentane. And we learned that they are actually not planar cyclic compounds in order for the atoms not to relieve the stress and steric factors and or to minimize on the repulsions between atoms. And the last cyclic compounds that we studied was the cyclohexane, and we've learned that there are different conformations of the cyclohexane. And among the different cycloalkanes that we studied, it was the cyclohexane that actually have uh, no angle or torsional strain for the atoms, particularly for the atoms in the atoms and hydrogens attached to our carbon in the chair conformation. But we've learned that there are different conformations of our cyclohexane. You can have the chair, half chair, twist both, half chair, and the chair conformation. And for the chair conformation, this is the one that is the most stable as reflected in its relative energy, potential energy of the molecules compared to other conformation and the very unstable ones that have chair formation. And in this conformation, in the chair conformation, all the angle strain and the torsional strain actually is minimized. That's actually almost none for 99% in fact of the molecules are estimated to be in the chair conformation. And there is actually no angle or torsional strain. We can see, especially on the staggered conformation of our atoms in the cyclohexane. And you can also study on the conformations of cycloalkanes in a higher form. You have the cyclohexane, cyclooctane, and the cyclonane. And other higher cycloalkanes also exist in the non-planar conformations. And the small instabilities of these higher cycloalkanes appeared to be caused by, again, the torsional strain and the repulsive dispersion forces between hydrogen atoms across their rings. We call it the transannular strain. And the non-planar conformations of these rings, however, are essentially free of angle strain. So if you look at into the bond angle, for instance, for the cyclodecane. So what is cyclodecane? From the word decane, no, it's made up of 10 carbons, greater than 6 carbons for the cyclohexane. The carbon-carbon bond angle actually, let's have the example. The cyclodecane is 117. And because of this, now you're expecting the carbon-carbon angle to be 109.5. It's more than 109.5. And this indicates actually some angle strain because it's also too much. No, there is an angle strain if the bond angle is less than its supposed bond angle or expected bond angle for a particular sp3 hybridized carbon. So if it's also more than its normal bond angle, this also indicates some angle strain. Why is that? The wide bond angles apparently allow the molecules to expand and thereby minimize unfavorable repulsions between hydrogen atoms across the rings, and therefore there is very little space in the center of the cycloalkane unless the ring is quite large. And calculations for the cyclodecane indicated that the smallest ring through which the CH2, the three carbons chain can be threaded and molecules have been synthesized. However, that large rings threaded and chains and that have large rings are interlocked like chains in a chain. And we call this type of molecules as catenates. They are especially for the number of carbon atoms greater than 18, no? You will have small rings mag-interlock siya on each other because of the large carbon chains. Okay, and we will go back to the cyclohexane. And we mentioned that the most stable cyclic compound is the cyclohexane, where there is minimal ankle and torsional strain. And we've learned in the previous discussion that the atoms bonded to carbon or the hydrogens bonded to carbons are classified depending on the spatial orientation of the hydrogen atoms. The hydrogen atoms are situated or extended from the perimeter of the ring. You call it the equatorial hydrogens. And the bond is in the equatorial bond. And the hydrogen atoms that are perpendicular to average plane of the ring, you call it the eggshell hydrogen atoms, the pink or eggshell hydrogen atoms, and the bond between this hydrogen and the carbon, you call it the eggshell bond. And for each phase of the cyclohexane ring, can have it up and down. We learned about that for it to satisfy the 109.5 for each hydrogen carbon bond. Now all of these bond angles for cyclohexane is actually 109.5. And to satisfy that, there is an alternate up, down, eggshell position, and alternate down, up, down also for the equatorial position. Okay, and I would like you to practice on how to write on the cyclic alkane, the cyclohexane. Okay, and you can write two parallel bond first, and then you draw down, you draw up, down Kenisha, and then you can draw up here for the chair. And you can have the eggshell. This point here, pointed carbon here is up, then you can have the eggshell up here, then equatorial down, and on this part you will have the eggshell down and equatorial up. And if you flip this ring, so this is carbon 1 and this is carbon 4. So if you flip this carbon 1 down, okay, all of this sigma bonds between carbon will also be rotated. As you rotate this, no, it will have to rotate, all the other carbon sigma bonds will have to rotate in order to minimize the rotation that is brought, or the strain brought by the rotation of this. And to relieve that, it will further satisfy the 109.5 steel bond angle. But it will happen from the up pointed here, carbon 1, it becomes down here. Okay, and carbon 4, we pointed up. And what will happen to the bond that is eggshell here will become eggshell up, will become equatorial up. And then the equatorial down will become eggshell down. And then the equatorial up will become equatorial, will become down. Here, I'm on 4. Equatorial up will become eggshell up rather. And the pink here, in carbon 4, it's down. It becomes down, but from eggshell it becomes equatorial. Okay, and we've learned about that. You just have to practice on writing the structure. Okay. So again, I have mentioned you have to learn how to draw on the chair confirmations. No, it's very easy. Just have to write two parallels first, and then you connect whether it's up or whether it's down. And we've learned also in the previous slides on the conformational analysis of the methyl cyclohexane. Okay, and you can draw on the Newman projection to see what will happen to our cyclohexane. So for instance, here you have your butane. Here, gosh, butane. Okay, and for the cyclohexane, you can draw two gosh here and connect the two many carbons? Four, no? Four carbons and five, six. You have two carbons that would connect the two Newman projections. And you can position your methyl group, methyl cyclohexane, the methyl group here to be up the axial position. And you can see that in the up or axial position here, there is the distance between the other hydrogen atoms is very close. And because of that, there is greater steric force or steric strain, no, exhibited by this bulky group, alkyl group here with respect to other two atoms. If you place this in the equatorial, like this position, methyl cyclohexane, so you have here, you just flip on. Okay, what will happen is you just flip, no? When you flip this carbon here, flip ni mo, kaya rotate man ang bond, carbon 1 and carbon 2, rotate ng kanan, no? So you have carbon 1 here, but up from eggshell, mahimo siyang equatorial, we've learned that. When we flip all the bonds, okay, and you will see here the position of the methyl groups is very far from all other hydrogen atoms. So you can see that in the equatorial position, there is a minimal repulsions between the hydrogen atoms and this methyl group here. And in fact, this is more stable. The equatorial methyl cyclohexane is more stable by 7.6 kilojoules per mole relative to the eggshell methyl cyclohexane. So it's also the same if you have other bulky groups. So here our bulky groups is methyl, but we can also replace this with other bulky groups, no, the third butyl, for instance. And the same thing will happen. You will always have to choose the equatorial position rather than the axial position of this bulky group. Again, for reasons that there is a minimum repulsion among the other atoms. And I think we have already learned about the cis strands, and the cis trans stereoisomers is a type of isomer where there is certain barrier between the cis and the trans. You need to break this bond in order for the CH3 here to be on the opposite side from the plane of the spring here. And because of that, there arise actually as what we call as the cis trans isomer. So this kind of isomer is also called the stereoisomer, where we can see that the connectivity of the atoms is still the same, only that there is that spatial orientation that is different from the other one. And you call it the cis trans cycloalkene, no? You can also do cis trans isomerism with your double bond, your alkene. And it's different, so you have to distinguish whether it's stereoisomer or they are just simply the conformational isomers. Conformational isomers would still be the same connectivity, and they will only differ in their orientation in space with respect to the rotation of the bonds. For example, here you have the 1, 2, 3, 4, 1 for cyclohexane, and you rotate this. This is in the axial position. You'll get your 1, 4 methyl dimethyl cyclohexane. And from the eggshell, they will be resorted to equatorial position. So you can also see that since it's in the trans position, when you flip the ring, you would still get the trans di 1,4 methyl dimethyl cyclohexane, 1,4 dimethyl cyclohexane. Okay, so these are what we call as conformational isomers. It's different from the cis trans isomer. So how do we know two groups are cis or trans? So a general way to recognize a trans disubstituted cyclohexane is to notice that one group is attached to the upper bond of the two to its carbon and the other by the lower bond. So for example, here, this is up. Okay, you have to know, like, between this two group of atoms attached to this carbon, you have to know, like, this one is down, this one is up. You can see here, this one is down, the other is up. So if this is up and this is down. The bulky group here on this carbon is up, and the bulky group on this carbon is down. So they are trans to each other. And you call this trans 1,4 dimethyl cyclohexane. Okay. And here you can see that it's in up and it is in up also. So the only difference is that here it's up, but it's in the equatorial position, and here it's up, but it's in the axial position. But in the same manner, they are still in the up position. So you have your cis 1,4 dimethyl cyclohexane. So you have your, so there are two types for 1,4 dimethyl cyclohexane. There are two types. They can be cis or they can be trans. Now let's go to the conformational analysis of our cis isomer here. Now you have to remember, if you are in the cyclic position, you can rotate all the bonds, and the equatorial and the axial position can then be interchanged. Okay, so if you flip this, if this is up, it will still be up. But from equatorial, it becomes axial. And here, when you flip this, maubos naman yung carbon from up, it will still be up, but from axial up becomes equatorial up. Okay? And then you will have to analyze which of the two conformations will be more stable. And here you will have one equatorial and one axial, and one axial and one equatorial. It's actually the same, especially if the bulky groups are the same, then therefore the two conformations are actually are equally important. And either of these two conformations is just the same, even if the ring flips. And I think I mentioned that there are other ways of writing whether our cyclic compounds are in the trans or in the cis. You can write from the top view. You can write a wedge towards you or a wedge away from you with a broken line. So for the trans, you can write the dark and the broken line. It means that they are, if the plane, this hexagon here is the plane, no? This dark one is protruded towards you, and this broken line is protruded away from you. Okay, so they are in the opposite side of the plane. You can say that this is the trans position. So the 1,4 dimethyl cyclohexane. Okay, and here you have on the same side two wedge. They're on the same side, so it's this, so you can write the broken. And you just have to check when one ring substituent group is larger than the other and they cannot be both equatorial, the conformation of the larger group equatorial will be more stable. So you always choose the bulky groups that is in the equatorial position, as there will be again minimal torsions with other atoms. Let's see. So here is trans. I think we've already discussed this. Trans one, you can see here, this is third butyl, this is methyl, okay? So you can see that the third butyl is in the equatorial or in the axial position. Annie, are you with me? Are you with us? Shalel. The third butyl, if you look at this structure, is the third butyl in the up or in the down position? Shalel. Like the name, Shalel. Oh, what about Carl Jean? Carl Jaira. Okay, walay mo. Okay. Mike, anyone? Here you have your third butyl. Is your third butyl on the up position or is it in the down position? Okay, so see Angelica is in the up and the other one is in the down. So therefore, Angelica, the third butyl 3-methyl cyclohexane is a trans isomer. Okay, if you flip this is up. You flip this, what will happen to the third butyl? Is it still up or is it down? May J. When you flip the ring, you flip this, the whole bonds here, what happens to the ring? Now what happens to the third butyl? Roglin? Okay, you can see okay, so you see that it's still up. So this second structure here is in the cis or is in the trans isomer? Anyone? The second is a trans or a cis isomer? Paningog mo. Vince. The second is trans or cis isomer? Vince, you want? Si Angelica Ragintao is tubag. Ano di ba na matingog? So it's in the trans. But which one is more stable, the first or the second? The first. And so that's the first. Okay, it's very easy. Why the first? So, of course, you know. So I think that's all. It's very simple. Write a conformational structure for 1,2,3 dimethyl cyclohexane in which all parts in which all of the methyl groups are eggshell and then show its more stable conformation. So when you are asked in the eggshell position, automatically you have to remember that to show whether they are eggshell or they are equatorial, you have to write the cyclic structure of the cyclohexane using the chair conformation. Okay? So how do you write? Of course, i-draw lang yun. Like this. You draw, it's in the eggshells, you draw two lines, okay? So two lines down, and then you make a point for the chair and a point down, point up, and a point down. And since all the methyl are in the eggshell, so you have to count if this is carbon 1, so it's up. Eggshell means yes. So 1, 2, 3. So magsunod siya. No? 1, 2, 3. You write eggshell up, eggshell down, eggshell up. Then you write CH3. Okay? And then you flip the ring. What will happen? I'll flip the ring. Okay? The structure that will be written is if this is two parallels down. Okay? Diri ang isa ka what happen is that when you get on the rings, okay, you will have the equatorial up, equatorial down, and then equatorial up, equatorial up, equatorial down, equatorial up. Okay, two are up, one is down. And the question is, show its more stable conformation. So how do we show its more stable conformation? Which one is more stable, the first or the second? Anyone? Write your answers. The second. Why is the second? Second. Kung para gitaon ang magsiging answer. Second. Why the second? Why second? Isa man eh. Why second, Alexi? Why is the second structure more stable? Second daw. So, which one is more stable? Nakabutang may diri ha, much more stable confirmation. Klaro de. Okay? So, much more stable confirmation, but sayop siya, dapat the ring should be diri, majority, ang arrow should be more diri as a right. Lang pagka-right sa arrow. The arrow, the larger arrow should be to the part where it is more stable. Okay, mo alam siya sa'yo. But the rest, this is more stable than this. Now, why? Because here you can see the CH3, CH3. They're very
Naka-eggshell
close
man.
together because of the
Ayun.
the eggshell. Because of that, there is a greater repulsion of the electron
Pag
density.
tanan sila naka-eggshell, na greater repulsion. Pag naka-equatorial siya, nakahigda, less siya ang charge na mag-repulse sila. Hindi. Hmm.
Okay. Write the conformational structure for 1-bromo-3-chloro-5 fluorocyanates in which all the substituents are equatorial. Then write its structure after a ring flip. Okay. So, ipadraw ta mo ani. That will be your practice problem. So, that will be your problem set. I will post that. And then you can also have the bicyclic and polycyclic alkanes. So when you have this bi and polycyclic, you can see that there is like a bridge between the two. Many of the molecules actually that we encounter and study in organic chemistry may contain no more than one ring. And one of the most bicyclic system is the bicyclo-4,4,0. So how do you know it's 4 by bicycle 4,4,4,0 decay. So I'm gonna say decay, you have to count. There should be 10 carbons. You have 6 here, 7, 8, 9, 10. But since it's bicycle, there is something that connects the two. So it's 0, but you can see 4 so which means before the bridge, there is like 1, 2, 3, 4 carbons and another 1, 2, 3, 4 carbons. And then you will have that here. There is 0 here. So there is only 2 rings here. 0 meaning isa. Okay. So this is your bicyclo. And here is a cis decalin, 10 decane decalin today. And the other is bicyclodecane. The other is they are on the same side. The other is they are on the opposite side. How do you know? No, you have your hydrogen here. The hydrogen here is eggshell. This is eggshell, but on the opposite side of this plane. So here you have the trans, and here, since they're on the same side, is the cis bicyclodecane, or common name is nickel. You can also write merging using the top view of the hexagonal form of our cyclohexane, no? So you have your cis decalin. You can write the cis, which means they are on the same side. So you can have this two wedge dark. Written dark means they are on the same side. towards you, or you can also write the broken line here. Parehas sila, diba? And in the trans, you can write here towards you and broken line. Paper. The other one, cyclic compounds, fuse, you have the adamantane. So how do you name this? So adamantane is a tricyclic system that contains three-dimensional array of cyclohexane rings. You'll see here, you can actually count that there are 1, 2, 3, like 6. No, you can have 1, 2, 3, 6, and on the other side, it's also like 6 carbons. Seems like 6 carbons. So it's a three-dimensional array of cyclohexane. I hope that you're able to follow. So if you check on this space, you have 1, 2, 3, 4, 5, 6. This space is 1, 2, 3, 4, 5, 6. Sa likod, if you view from this side, sa likod, you can see that it's 1, 2, 3, 4, 5, 6 also. Okay? So let's go to the reactions of our alkanes. The common reactions of alkanes, if you look at its structures, you don't see actually electrons, no? And in fact, your alkanes, because there are no electrons on carbon or on the hydrogen, it's actually very stable and it's very unreactive. It cannot act as an acid, it cannot act as a base. And because of that, there is very low reactivity of alkanes towards many reagents. If you remember in our introduction, no, that having an extra electron, unshared electron, it will make our organic compounds to be reactive towards other species that would have available orbital to accept electrons. In the case of our alkanes, okay, the case of our alkanes, this is the cyclic. You don't see an atom that has an extra pair of electrons. It's very unreactive towards many reagents. And because of that, we call it paraffins. The alkanes are called paraffins. In Latin, it's parum affinis, or little affinity to all other agents. So, unsa na the reactions ni alkanes? We will check later, but the common one you have already encountered at home and in the general chemistry, no, it's the combustion reaction. But how do we prepare our alkanes? So the preparation of our alkanes normally came from the hydrogenation, this word, from our alkene. So if you see a double bond, we can actually convert this to alkanes. So what is a hydrogenation reaction? The reactant here from the word hydrogenation is actually H2, it's a hydrogen gas. To react in the double bond to get your alkane part here, carbon, hydrogen, nitrogen, CH double bond. But for this reaction to proceed, there will be a catalyst that is included. Normally, you have the platinum, palladium, or nickel. It's actually a metal. So when we write here, we can write on to insert. You can write here your hydrogen gas, okay, in the presence of your platinum, palladium, or nickel metal. Okay. Okay. You have your hydrogen gas. It's a gas in the presence of the other metals. So here is an example of a reaction that is used in perfume. We started with a cyclic compound with a double bond, and then you have here an ester, and it will be converted without double bond here. So equations. The equations in the reactions represents the general examples for the hydrogenase. And again, I mentioned that you will have to need a catalyst. So what is the general equation for the conversion to the alkanes? You usually start with an alkane. You have a double bond. In the presence of a hydrogen gas, it's H2. In the presence of a catalyst, you have a platinum, palladium, or nickel, and in a solvent and very high pressure, and then you can add this hydrogen to the double bond here, and you will be able to eliminate on the double bond. You get your alkane here. You can also see this reaction in the alkyne where you can eliminate the triple bond, and you will get 2 moles of your hydrogen to be added here. So you have your hydrogen, hydrogen, hydrogen. You can see that carbon still satisfies on the octet. So normally the catalyst for alkyne for the hydrogenation reaction is the platinum. You can have specific examples. You can have double bond. Now you have your hydrogen, and in the presence of a nickel, you have your solvent. Normally it's ethanol. And at 25 degrees Celsius, 50 atm, we have to remember that our normal atmospheric pressure is 1 atm. So if you have a reaction at 50 atm, it's very situated in a very high pressure. So you do this reaction at a very high pressure to convert your double bond here to get your alkane. So you add your hydrogen here and you get your alkane. Also see your cyclohexene. You have your hydrogen in the presence of a metal. Here it's at normal atmospheric pressure. You can already get your alkane here, cycloalkane. And you can see also here in the alkyne, you can see the triple bond, and you need 2 moles of your hydrogen to eliminate this triple bond here. Okay. And so your normal solvent, normally you have ethanol, but you can also have the other organic solvent, which is MP. So that's a normal reaction. The first reaction, write the structures of 3 pentenes that would all yield pentane on hydrogenation. It's very simple. You write pentene. So remember your pentene, you can have your 5 carbons, and then you will have your double bond. Your double bond, you can have an isomers of pentene depending on the position of the double bond. So you can have the positions of double bond on the first carbon, and the second carbon, or the third carbon. Okay. So you can have your 1 pentene, you can have your 1 to 2 pentene. And actually for 2 pentene, there are 2 types of pentene. You can have the cis or you can have the trans. So what is the cis and trans pentene? If with respect to the double bond, the bulky groups are on the same side, you call it the cis. If with respect to the double bond, the bulky groups such as the methyl and this are on the opposite side, it's a trans pentene. Now, if you have your double bond here, balik diri, it still actually be 2 pentene because symmetric man siya. So there's 3 alkane that you can write actually. So wala na itong 3 pentene. You only get 2 pentene. Wala na itong 3 because 3 pentene is just 2 pentene. Okay? So you have 1 pentene, cis 2 1 pentene, and trans 2 pentene. If you add hydrogen gas in the presence of a metal, platinum, palladium, or nickel, in the presence of a solvent at some pressure, you actually yield your normal pentane. So eliminate this. So during this reaction, we need to know the index of hydrogen deficiency of our molecules. So normally a chemist working with an unknown compound can obtain information from the structure based from the compound's molecular formula. So what is the molecular formula of the compound? Normally you just have to know how many number of carbons and number of hydrogens, number of atoms, or number of atoms for each type of atom. And we need to know the molecular formula, and we need to know the index of hydrogen deficiency. What is the index of hydrogen deficiency? It is simply defined as the difference in the number of pairs of hydrogen atoms between the compounds under the study and a cyclic alkane having the same number of compounds. So example, if you have the saturated acyclic alkane, so instead ng acyclic, it's the normal alkane, no? Or the unsaturated hydrocarbon. So you have the general formula I'd like to highlight. It's CnH2n. Okay? It's CH into. So for example, if you have two carbons, so carbon 2, you have your formula C2H6. So you have 2 times 2, 2 times n. If you have n, is 2. 2 times 2 is 4, plus 2 is 6. So you have C2H6. That would be your general formula. Okay, so when we calculate for the index of hydrogen deficiency, we have to know the difference in the number of pairs of hydrogen and with respect sa acyclic nga alkane from this. So what is the rule? Each double bond or ring reduces the number of hydrogen atoms by 2 as compared with the formula of the saturated compound. And thus, each ring or double bond provides 1 unit of hydrogen efficiency. So example, let's see here. Okay, so you will see here that in this alkene form, wala siya hydrogen. So if this is actually ethene, no? If you have hydrogen, hydrogen, hydrogen here, this is C2H4. If this is hydrogen, hydrogen, hydrogen here, if this is ethane, no, this is C2H6. So what is the difference between this, the molecular formula of this alkane and the molecular formula of this compound? So we need to know the difference. So what is the difference, for instance, for the number of hydrogen? The difference is that there is actually 2 hydrogens missed in alkene as compared to your alkane, because when it becomes an alkane, you added 2 atoms of hydrogen here. Okay, so when we calculate for the index of hydrogen deficiency, we need to know the index of hydrogen deficiency. So we have to count each double bond reduces the number of hydrogen atoms by 2 as compared to the formula. And therefore, each ring or double bond provides 1 unit of hydrogen deficiency. So let's have an example. If you have 1-hexene and cyclohexane have the same molecular formula, okay? So you notice this is 1, 2, 3, 4, 5, 6 carbons, and the hydrogen is 2, 3, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 hydrogens here, and you calculate also for the molecular formula, it's still C6H12 for cyclohexane. So if we are to calculate what is the index of hydrogen deficiency for 1-hexene and cyclohexane, you have to check on the difference from the normal or corresponding alkane. So what is the corresponding alkanes for this? So learn that this is carbon 6, there are 6 carbons. So you follow on the formula CnH2n plus 2. So you expect that for a normal alkane or the acyclic alkane, okay, you have the C6H14 because C6 times 2, 12 plus 2 is 14. And here you get C6H12. So the difference between the two, the normal alkane here and the C6H12, it's 2 hydrogens. So therefore, there is a pair of hydrogen atoms, and therefore the index of hydrogen deficiency is 1. So if you have your alkynes and alkadienes, now what is alkadienes? Contain 2 double bonds. It actually has the general formula of alkynes as CnH2n minus 2. And if you have your alkenyls, the general formula is CnH2n minus 4. So what is the formula for an alkene? So if it's C6, the formula actually is just C6 CnHn times 2. So it's the formula for alkene is simply, of course, you know that CnH2n lang. You can calculate if carbon is 6, then the hydrogen will be. But for alkynes, it's minus 2. Okay. So the question is, what is the index of hydrogen deficiency for 1,3-butadiene? Okay, what is the index of hydrogen deficiency? It says here it's 2. So how do you calculate for 2? So you have to calculate for a normal. Okay, for a normal 4 carbon atoms, it's C4H filaman. So you have the corresponding alkane here. You will have your C4H pila. 1, 2, 3, 4. Anyone? 2n plus 2. So it's 4 times 2, 8. You will have your 10. Okay? And for your alkene, you will have, for this alkene, still have C. Okay, okay. For your hydrogen here is 2, 3, 4, 5, 6. Okay? So therefore, your IHD, the difference S between the two is you have your H4. Okay? So since it is H4 for every hydrogen efficiency, so there is a pair of 2 hydrogens. So you actually have 2, your IHD is actually 2. So the general formula here is that each double bond or ring reduces the number of hydrogen atoms by 2 as compared with the formula for saturated. Okay. So again, the IHD is defined as the difference in the number of pairs of hydrogen atoms between the compounds. It's actually a pair of hydrogen atoms. So since it is a pair, you can see here that pair is for every index of hydrogen deficiency, it's a pair of 2 hydrogen atoms because it's H2, and therefore the IHD or the index of hydrogen deficiency is 2. So therefore, if you know the index of hydrogen deficiency, if it's 2, then for every double bond, actually, there is one pair of hydrogen that's being eliminated. And because here the index of hydrogen deficiency is 2, you expect that there is 2 double bonds. You can also calculate from here the index of hydrogen deficiency. So it's the same manner as how you calculate from here. Calculate from here. How do you calculate for that? So here you have 1, 2, 3, 4 butane. 1, 2, 3, 4. It's still 4. But for the alkene, Y and E here, you have to count. Okay? So how do you count? So you can count. You have 1. This is a double bond. You have 1 hydrogen here. You have 1 hydrogen also here. 2 hydrogens here and 1 hydrogen here. So that's 3. And you have 1 here, hydrogen. So you have actually 4, right? more hydrogen. So the difference between H10 and H4 is actually H6. But a pair of hydrogen man ang IHD, so 6 divided by 2 because pair is 2, so you actually have a 3 index of hydrogen deficiency. So how do you see that? No? So you expect, since you only have 1, 2, 3, 4 carbon atoms, you expect that you have an isa, the double bond, and then you have a triple bond here. So you can calculate also for this. You will get your, as a general rule, the index of hydrogen deficiency is easily determined by comparing the molecular formula of a given compound with the formula for its hydrogenation product. And each double bond would consume 1 molar equivalent of hydrogen. So it's a gas, it's H2, and counts for 1 unit of hydrogen deficiency. So you've seen that one. And each triple bond consumes 2 molar of hydrogen atoms and counts for 2 units of hydrogen deficiency. And since rings are not affected by hydrogenation, each ring still counts for 1 unit of hydrogen deficiency. So double bond or a ring, it counts for 1 unit of hydrogen deficiency. Therefore, you can see in the previous reaction that hydrogenation allows us to distinguish between rings and double or triple bond, no? Depending on the hydrogen deficiency. So let's have an example. As we've learned that hydrogen allows to distinguish between rings and double bonds, consider the reaction of 1, 2, 3, 4, 5, 6, 1-hexene to produce our alkane here. So in the presence of hydrogen, presence of a catalyst, certain temperature, and some pressure, okay, you can convert the double bond, the alkane, into our alkane here. Again, this kind of reaction is the hydrogenation reaction. And if you have a ring in the presence of hydrogen, there is no reaction here. So how do we distinguish the two? Now you can distinguish the two from its index of hydrogen deficiency also, no? And you can see that here the index of hydrogen deficiency is 1. You can calculate with that. Here, the index of hydrogen deficiency is also 1. Okay. And for a ring, there is actually no reaction with our hydrogen gas. You can also have another example if you have your cyclohexene and cyclohexene in the presence of your hydrogen. You can do hydrogenation reaction. In the hydrogenation reaction, we can eliminate the double bond. You can see here all saturated alkane here. Okay, and you can count for the index of hydrogen deficiency for this one. And here you have your 1,3-hexadiene, okay, to form your alkane, but you need 2 molars of your hydrogen gas to form this one. So these compounds both react with hydrogen in the presence of catalyst, but cyclohexene, because it only has 1 ring, it only has a ring, no, and only 1 double bond, the ring does not react to the hydrogen. So you only need 1 mole of your hydrogen gas. So in here, the index of hydrogen deficiency to produce this one is only 1. But if you have double bond here, the index of hydrogen deficiency, you needed 2 hydrogens. Okay, hydrogens. So you will have your problem set. What is the index of hydrogen deficiency for 2-hexene, your methyl cyclopentane, and the index of hydrogen deficiency reveal anything about the location of the double bond? Or does, it's a question. Does the index of hydrogen deficiency reveal anything about the location, about the size of the ring? What is the index of hydrogen deficiency of 2-hexene? Okay. Now you can practice on this, so knows I'm gonna be giving a quiz for this. The other is In general, what structural possibilities exist for a compound with the molecular formula C10H16? So for this letter F, you have to know what is the index of hydrogen deficiency so you can have possibilities on what to write. Like, can you have a ring? Can you have a double bond? How many double bonds can you write? Can you write the triple bond in the structure? So you have to calculate to know on the index of hydrogen deficiency, and you know how to calculate on the index of hydrogen deficiency. So if you have 10 carbons here, so you have calculate from the molecular formula for a normal alkane. Okay, it will be C10H20 plus 2. It will be H22, and you can have 22 minus 16. So what is the difference? And you can calculate for the IH. Now, in cases where you will have other compounds containing containing halogens, oxygen, or nitrogen, how do we calculate for the index of hydrogen deficiency? So, for example, if you have C4H6Cl2, what is the index of hydrogen deficiency here? So in this case, we count the halogen atoms as they were hydrogen atoms. So even if it's Cl2, we presume this is hydrogen. So you can count this as if it's C4H8. Okay, and then you calculate for the molecular formula for a normal alkane. So since if you have 4 carbons, you will have C4H10. And then the difference between C4H10 and C4H8, it's 2. So since it's 2, it's equivalent to a pair. So the index of hydrogen deficiency is 1 for this. Okay, if the compound adds one more equivalent of hydrogen and catalytic hydrogenation at room temperature, then it must have a double bond. If it does not add hydrogen, then it must have a ring. This is what we can tell from a hydrogenation experiment. Okay, if it does not add hydrogen, then it must have a ring. If it adds, then it must have a double bond or a triple bond. So what about if you have oxygen in the structure? How do we calculate if there is an oxygen in the structure? For example, C4H8, how do we calculate for the index of hydrogen deficiency here? So for this, we simply ignore the oxygen atoms and calculate the IHD from the remaining of the formula. So if this is C4H8O, this is the molecular formula, we simply write as C4H8, and then we subtract from the normal. So the normal for C4H8O, it's pilaman. It will be C4H10 minus C4H8. It's actually H2. So 2 hydrogen, it's a pair. So therefore, the index of hydrogen deficiency is 1. So how do we write on the structure for this? So you can expect that it may have a ring, it may have a double bond kay isa naman. Okay? So you can write 4 carbon atoms. You have 1, 2, 3, 4. Okay? And then you have your OH. And then you can write a double bond here, or you can write a double bond here, second carbon, or you can write the double bond on the oxygen. Okay, you can write the double bond here if the oxygen is here. Now you can write the double bond diria. Okay, or you can have it cyclic 5 rings, or you can have it cyclic 4 rings, and so on. So this is how you can actually predict, possibilities on the structures that you can write based from the index of hydrogen deficiency. So for compounds containing hydrogen atoms, how do we view them? So for compounds containing nitrogen atoms rather, like C4H9N, we subtract 1 hydrogen for each nitrogen atom, and then we ignore the nitrogen atom. For instance, you have C4H9N, so for us to write or to predict, you ignore the N, so it's as if you have C4H8, and then you subtract this from the normal alkane, which is C4H10, so H10 minus H8, it is H2, so it's a pair. Therefore, the index of hydrogen deficiency is 1. You can expect that you can have a double bond, 1 double bond, or 1 ring. Okay, so you can write 4 carbon atoms. You have 1, 2, 3, 4, and then you have your nitrogen, NH2. You can write the double bond here. You can write the double bond here, second carbon, or you can write the double bond here, or you can have your nitrogen here, and you can get your double bond here. Or you can get your NH here, and you can get the double bond here. You can have the double bond here. Or you can have the ring, 5-membered ring. You can have the ring, 4-membered ring, and so on. Okay? So knowing the index of hydrogen deficiency actually allows you to write structures, predict structures, any structures as possible. So in general, now what are the applications that we've learned so far in chapter 4? We've learned that the nature prefers states of lower potential energy, and that is when most of the time would our molecules stay in that state. And in the conformational analysis, you can see that the lowest potential energy of such conformation will allow the compound to be staying in that state at equilibrium. And we've learned that the staggered conformation is preferred because of its low potential energy. And we also learned that the anti-conformation of butane and the anti-conformation of the chair are preferred conformation again because of there is a lowest potential energy. Now, why would it have lowest potential energy? We've learned that the very reason that we have very lowest potential energy now because there is minimization of the repulsion between atoms or group of atoms in the structure. Any questions? And we also learned that disubstituted cycloalkanes prefer a conformation includes both substituents. And they prefer a conformation in the equatorial position because the equatorial conformation or position for bulky groups and substituted alkanes provides or exhibits the lowest potential energy. Another factor or effect that we encountered is the steric factor. You have the spatial factors that affects the stability. Any unfavorable interactions between groups are central to explaining why certain conformations are higher in energy than the others. But you can think of this as the like charges repel. Now, if you have alkyl groups and alkyl groups close to each other, they will always likely to repel each other. And we've also learned that repulsive interactions between the electrons of groups that are in close proximity causes the conformations to have higher potential energy. And this is what we call actually as the steric currents. That provides strain. And so yes, that's all for chapter 4. Any questions? Congratulations, we are done with chapter 4. And for this, you saw this in the PowerPoint. You saw this in the LMS. Okay.